Okay then, should we make a start and any stragglers can kind of come on in? Okay, so welcome to the session on carbon cycle. I'm Gareth Clay, one of the lecturers in physical geography here in the department. And I'm kind of going to hopefully give you an overview of some of the material that I teach here at Manchester to a range of different years, first, second and third years, on the carbon cycle, climate change, and how they all interrelate. So I'm going to kind of give you lots of slides, lots of diagrams, lots of images. They'll all be available afterwards, so don't worry too much about getting everything down on paper. But hopefully it'll kind of inspire you to go away this afternoon and discuss how you might want to transfer this into classroom activities or fieldwork activities. I've got some ideas, some suggestions, which I'll kind of drop in throughout the session. So I'll kind of talk for about an hour and a half or so. I've got a few activities, but if you want to ask me any questions at any point, please just put in and ask for clarification. So this is kind of a distillation of a third year course that I teach called Climate Change and Carbon Cycling, a distillation of some first year lectures on soil science and a few other bits and pieces thrown in for good measure. So there will be activities, I will be getting you involved in a little while. So as I said, I'm Gareth Clay, lecturer in physical geography. I started out as a geologist. I didn't start out as a geographer, and my confession for today, I didn't do A-level geography, I did A-level geology. I know it's heresy in front of a field full of geographers. But I slowly transitioned towards environmental science, towards geography, and into physical geography over the last 10 years or so. So I started out as a geologist, but moved into the role of land management, the role of peatlands here in the UK, and then in the last 5 years or so, more globally, the role that soils play in cycling of carbon between the atmosphere, the biosphere, and in part down to the oceans. So research specialisms in fire, land management here in the UK. I do get to go on some nice little jollies around the world. So this is a lovely waterfall in South Africa where we were out sampling some soils. But equally, I do get the wonders of peat bogs in Salford when it's tanking down with rain. So I've got a real strong interest in carbon, in climate change, in the role and the interaction between the two. So why is the carbon cycle important, and why, having listened to Martin's lecture a few minutes ago, why is carbon so important to bring into the A-level curriculum? Well, it's a global process, a global cycle. It's something that interlinks many, many cycles. The water cycle is fairly familiar, the carbon cycle may be familiar as well, but it's a way of unifying a whole range of processes, a whole range of activities and so on. And it's where we can study, like Martin suggested, we can look at local processes to infer things about the global. So your students can go out to the local field, measure the amount of grass in the field, and calculate the carbon content of that grass. Real simple things, but looking at global activities. And it mirrors and kind of meshes together with a whole range of contemporary and current concerns in the science, media and policy that we're always seeing in papers, in policy reports, whatever it might be. Climate change. Big story in science, big story in the media, massive global shifts in the way the planet is working. Carbon is at the heart of that. Land management, okay, how we manage our land around the planet has a direct bearing on how carbon is stored or not stored in some cases. So the conversion of tropical land, for example, for oil palm plantations shifts the amount of carbon in the soils, for example, and moves it to the atmosphere, for example. And resource use, okay? There's a whole raft of other examples, but resource use, how we effectively and sensibly manage our landscapes. So the big campaign at the moment, or has been going on for years, but it's kind of picking up steam, is the reducing of horticultural peat in compost. Who, when they're doing their gardening, goes out and specifically looks for peat-free compost? Some people do. Who knew there were things called that is peat-free compost? Okay, a lot of the commercial grade compost in B&Q and Homebase, around about 50-60% peat mined or milled from places like Ireland and Estonia and Russia, for example. And that peat, that carbon, is being used in your gardens. Okay, so there's a whole raft of current issues that the carbon cycle can be linked to. But we need to know something about the process, something about the underlying physical geography, underlying physical sciences, so that our students at A-level and university can understand something about these contemporary issues. So it's important for a whole raft of things. I'll kind of flick through these slides, but this is a generalised schematic of the climate system, looking at forces, how the system responds, and then the output being the variation. So again, bringing everything to the system's way of thinking, modifying any forcings, you affect the system, and you affect a change in the output. And the big thing at the moment is if we modify various different components, and we're thinking specifically about greenhouse gases, modifying the atmospheric chemistry, we will affect a change in the global system. So understanding the carbon cycle and how it interrelates with the climate system, for example, is very important when we're trying to tackle some of the root causes, mitigation, adaptation. So how we tackle the root cause of climate change through mitigation and adaptation. So that's kind of the big picture. So carbon cycling. Who here has studied carbon cycling in the past at any stage? Yeah, whereabouts? Where did you study that in terms of your education?
The last 2 years, because I had to teach environmental science.
Okay.
So that's part of the degree because we was environmental science, right?
Okay, so part of the degrees in environmental science. Okay, anyone else?
Again, part of the degree.
Part of the degree program. So it may be part of people's degree programs. It may also have been part of their GCSEs and A-levels in the sciences, the chemistry side of things. It often gets moved across with some of the kind of the biology and the chemistry. It's obviously not taught in geography as such until the new specification. So you may recognise simple diagrams like this. This is the CO2 cycle, a very simple kind of GCSE, pre-GCSE cycle. Showing how CO2 moves from the atmosphere through photosynthesis into organisms. Those organisms decay and die and become fossils and fossil fuels, and eventually get exported through factory and auto emissions. This is the American slide. But that kind of belies a much more complex picture, that it's not just about CO2, it's about other forms of carbon as well, and it's about how they all interlink. And part of the curriculum, part of the syllabus, is to look at these stores of carbon, these reservoirs or stocks of carbon, and how carbon moves between these stores through these flows or pathways or fluxes. There's lots of different terms that are banded around. I think in the DFE guidance and some of the what is it called? Stores and flows, I think it's in the curriculum. I would refer to it as stocks and fluxes, but they're all interchangeable. The amount of stuff and how it moves between the two. So one of the first activities I'm going to get you to do, so I'm not going to talk for all of this session. Part of the curriculum is for students to know how big these stocks, how big these fluxes are, the relative sizes, how it moves between each, which one's the biggest, which one's the smallest, and so on. So I've got a little activity here. So here we have the diagram from the IPCC, so the Intergovernmental Panel on Climate Change, from their 2007 assessment, fourth assessment report. And in it, I've blanked out most of the carbon reservoirs, the stores, and I've blanked out most of the fluxes, the pathways, the flows. I've only given you two, okay? It's a real harsh, nasty thing to be making me do at 11 o'clock on a Friday morning. But I've given you two, okay? I've given you the rough size of carbon in the atmosphere, nearly 600 gigatons of carbon. And I've given you the emissions from fossil fuel, which in this diagram is around about 6.5 gigatons of carbon per year. It's actually closer to 9.5, 10 now. I mean, this is only 8 years old or so. 10 years old now. And what I'd like you to do, doesn't matter about the actual numbers, but try and estimate the relative size of these different fluxes and of the different pools. So for example, our vegetation, soil and detritus, is that bigger or smaller than the amount of carbon in the atmosphere? Is the amount of carbon moved between through respiration, for example, bigger or smaller than the amount of carbon emitted from fossil fuel burning. It's a real challenging thing first thing in the morning. For reference, the black lines are natural fluxes, things that are happening anyway. The red lines are anthropogenic fluxes, things that have been modified by man. So fossil fuel emissions is a direct emissions from man, but the two red lines on the land use and the two red lines on the ocean are how additional fluxes have been modified by man. So 5 minutes, doesn't matter about the numbers, but the rough relative size of these fluxes, and let's see if there's any kind of consensus with the actual numbers. Gross primary productivity, photosynthesis. Okay, how are we doing? Another couple of minutes? Gross primary Okay then. we've had a bit of discussion about the relative size of these. What I'll do is I'll reveal them in a second. So the actual line from the DFE specification is the students should know the distribution, the size of the most important stores of carbon in the land, the oceans, and the atmosphere, and the factors driving these changes, driving change in the size of these stores over time and space. So we'll kind of discuss those as we go on. Now that was a horrible exercise, I have to say. I talked to a colleague yesterday and said, "What, you're going to make him do that on Friday morning?" But this is a kind of a simplified exercise that you could do, your students, or some other similar exercise about relative sizes of these stores and of these fluxes. So, the atmosphere, around about 600 gigatons of carbon. Fluxes of fossil fuel to the atmosphere, somewhere around about, nowadays, somewhere around 9.5 gigatons of carbon to the atmosphere. So let's pick on a couple of these stores, a couple of these fluxes, and we'll kind of give some estimates.
Sorry, excuse me, just before you dive on. Gigatons is 12 zeros?
Yes.
Okay.
So, megaton, kiloton, megaton, gigaton, billion tons.
Billions?
Billions, it's 9, isn't it?
9?
Yeah,
Right.
I should know this. So often, certain things like the IPCC report will use units like gigatons of carbon. More recent IPCC reports are using petagrams of carbon. Okay, that's exactly the same as a gigaton. So unit conversion is certainly in these large numbers something you need to pay attention to. Something that students certainly even into third year still can't get their heads wrapped around. So vegetation, soil, and detritus. How big do we think that might be? Any guesses? Any estimates relative to the atmosphere? 100.
Quite big, but we don't have a number.
Yeah. Numbers are irrelevant, but are we thinking twice the size of the atmosphere, 3 times, 10 times? Bigger, okay, we'll go with bigger then. The answer is bigger, okay, and we'll come to that in a second. I'll show you. It's about 2,300. Fossil fuels, how much carbon have we got locked up in our stores of fossil fuels, do we think? Huge. 3,700. Okay. Surface ocean. Any suggestions for what's stored in the upper 700 metres of the ocean?
Does that include sort of like just any organic matter?
Yeah. It's all organic matter in the upper 700 metres.
Yeah.
So plankton, organisms, everything.
Yeah. 2,000?
Not that much, about 1,000, just under. Because it's the deep ocean, the intermediate and the deep ocean, that is much, much bigger, on the order of 37,000. Okay? So one of the things that you can do, or one of the things I certainly do with my students, is take an idea, amount of carbon in the atmosphere, for example, and start to do relative sizes of these stocks and fluxes. So we've also got the flux of carbon from the fossil fuels to the atmosphere, around about 6.5 in this diagram, so it's closer to 10 now. And we can compare that to natural fluxes, okay, so things like respiration from plants and other organisms is around about 120 gigatons. The flip side of that is photosynthesis, or GPP, gross primary productivity, is also around about 120 gigatons of carbon. So they're more or less balanced each year, okay. Now on top of that we've got things like land use change, absorption or sequestration, of carbon through land use sinks and so on. So you can start to get a sense of how big some of these natural processes are, these natural carbon fluxes, and how big some of these anthropogenically modified carbon fluxes are as well. So that's the global scale thing. I mean, I'll put a copy of these slides on the website afterwards so you can have a look at it, but all these diagrams are available from the IPCC.
But why is the intermediate and deep ocean so big if that's sort of below the photic zone? Is it just because of the amount of water there is there?
It's the sheer volume, but also, if you think about it, it's particle rain, so you've got all the organisms dying and decaying, and it's also the inorganic component as well, so we'll touch on the oceans in a little while.
Right.
Yeah. So these diagrams, a lot of information, certainly with lots of nice visuals, available from the IPCC. So their website is www.ipcc.ch, they're based in Switzerland. And there's also another fantastic organisation called the Global Carbon Project. And every year they create a state-of-the-art carbon budget, lots of diagrams, lots of visuals, lots of useful material. We'll come to that in a little while. So just to note, the amount of carbon locked up in the biosphere is 3 times as much carbon as is in the atmosphere. We often think of the atmosphere being perhaps the big reservoir of carbon. The answer is no. Things like the biosphere are particularly sensitive or particularly large relative to the atmosphere. So anything that happens on land in terms of land management, the way we look after our ecosystems, has a direct relation or direct bearing on that carbon store. And the flux of carbon from the annual flux of carbon from the biosphere to the atmosphere and back again is on the order of a couple of magnitudes bigger, or a magnitude bigger than the flux of fossil fuels from anthropogenic activity. But what we've got to remember is the flux of carbon from anthropogenic activity is only going one way, only going into the atmosphere. So you can start to get a sense of scale, you can start to get a sense of magnitude, and we can start to realise that certainly things like the biosphere, vegetation, biomass, soils and so on, are very sensitive to these natural changes, but also anthropogenic changes as well. So things like soils, this is a slide that I used for the first years, bit of a guessing game similar to the previous exercises. Where do soils fit within that hierarchy? Some of these slides I hid because I was part of the exercise. Where do soils land within that? And they might put it somewhere down the bottom, but actually it's bigger by an order of magnitude, at least 2 to 3 times the amount of carbon in the atmosphere. So one of the big kind of pushes towards bringing all this together, as I said, is the Global Carbon Project. And every year they produce lots of really nice visuals, lots of really nice information, freely available PowerPoint slides and resources, all under the Creative Commons license. And this is a really neat way of kind of bringing that diagram together, bringing that complicated schematic together to look at the amount of carbon emitted through anthropogenic activities and where it goes to. Okay? So on the top of the diagram we've got all the carbon emitted through fossil fuel emissions, for example, cement production, as well as land use change, and where that goes to. So it's the apportioning of carbon dioxide between the atmosphere, the oceans and the biosphere. And that's the key thing. It's about where does it go to, how do those spheres interact with the atmosphere, so how does the land sequester carbon, what do we do on the land and how that affects its ability to sequester carbon, and the ocean and the atmosphere and so on. So it's a really neat way of showing how it progresses through time. We can look at regional carbon budgets, we can look at national carbon budgets, so we can look at it in space as well. And I use this diagram almost every lecture in my third year course to keep reiterating that it's a space and a time issue as well. So again, this is freely available from the Global Carbon Project. There are academic papers that underpin it. But a really nice visual of how our emissions are being absorbed, sequestered into the land, the ocean, and then the residual left in the atmosphere. So we can start to look at how this is broken down. Okay, so again, the Global Carbon Budget does this every year, and they update it every year. It's a really nice, for me, really nice technical paper. But they produce really good synthesis reports as well. So about 90% of all anthropogenic emissions are through fossil fuel emissions, around about 10% from land use change. And of that, around about 40-45% remains in the atmosphere. Okay? Nearly half of it remains in the atmosphere. The other 30 and 25% respectively are taken up by the biosphere or taken up by the ocean. And the big question is, how long is the biosphere and how long are the oceans going to be effective carbon sinks? How do they change under future climate change? What will happen to them over the next 200 years or so? Then how does that then feed back into what's left in the atmosphere? What does that mean for global warming? And so on. So we can look at how these have changed through time. Again, all of these are available through the Global Carbon Project. So when we're thinking about the kind of the geography of this, the kind of the interesting cases and the interesting examples, this one always sticks out for me. It always sticks out for me. So this is land use change emissions over the last 50 years or so. Good news story is land use change emissions are declining over time, slight upturn in the last few years or so. But there is a major anomaly. The major anomaly in the graph, in around about 97, 98. Does anyone know what that might be associated with? Massive spike of carbon to the atmosphere through land use change. It was the 97, 98 El Nino year, causing substantial release of carbon from forest fires in Indonesia, exactly. And that sits out like a sore thumb every year, and I use it as a case study of how significant land use change, significant interaction with climatic variability can lead to substantial changes in the carbon cycle. And we can pick out things to do with volcanoes, wildfires, particular regional events as well, all being picked up in these global signals. Be interesting to see what happens this year in the global carbon budget relative to the fires we had last September in Indonesia as well. So again, we can pull all these apart, we can look at them over time and so on. So in terms of the syllabus, in terms of the specification, we need to kind of look at where the carbon goes to, the different spheres, so atmosphere, biosphere, oceans, geosphere. I'm not going to spend much on the geosphere today, but we can look at weathering, chemical weathering, and so on. So what I do with my third year course, I split my course into three great spheres, the atmosphere, the oceans, and the biosphere. We tackle those in turn over the course around about 5-6 weeks or so. We look at the chemical processes, we look at the different ways that carbon interacts in those different spheres, and importantly, the controls on processes moving carbon between those great spheres as well. So I've talked for 5-10 minutes or so. Another quick activity with your neighbour. What I'd like you to think about is how can carbon get into the atmosphere? Okay, how does carbon, what processes, what mechanisms can carbon get into the atmosphere? Okay, and the second slide will be how does carbon get removed from the atmosphere to the other spheres as well. So what are the processes, the mechanisms by which carbon moves between the different spheres? So 2 minutes with your neighbour, how can we get into and out of the atmosphere? Okay then, 2 minutes up. How can carbon get into the atmosphere? What processes, what mechanisms can it get into the atmosphere?
Respiration.
Respiration, fantastic. Okay, how else?
Deforestation.
Deforestation, how? What's the...
Because the trees, for example, talking about rainforests, like carbon sinks and so they would absorb carbon dioxide. So if we chopped the trees down, then there would be more carbon released in the atmosphere.
Yeah, they decompose and respire their carbon to the atmosphere. Yeah. What are the mechanisms, what are the processes?
Combustion.
Combustion, yeah, fossil fuel combustion. Okay.
Volcanic eruption.
Volcanic outgassing.
Weathering processes.
Weathering processes, yeah. Animal respiration, we'll include ourselves in that, and plant respiration as well. Decomposition by fungi and bacteria, so breakdown of those logged forests, for example. Flatulence, always a fun one to talk about with students. Volcanic outgassing, metamorphism, release of methane hydrates, we'll come to that in a little bit. Degassing from ocean water, and many more besides. So it's not just respiration, it's not just fossil fuel emissions, but those are some of the important ones. There's lots of other subsidiary ones that you could investigate as well. How do we remove carbon from the atmosphere? How do we get it sequestered somewhere else?
Sorry, just going back.
Yep.
You know on this diagram there's a red line coming up from the surface ocean to the atmosphere. What process is that?
So that's probably a combination of, with warming the seawaters, you degas CO2. Colder waters allow more CO2 to be dissolved. So as you warm them up, you degas them. And if you can assign a particular, you can assign that warming to anthropogenic activity, that's probably where they divide that line. So I'm not an expert on oceanography, I have to say. So removal from the atmosphere. What are the processes again that we could remove carbon from the atmosphere? That will put it into the atmosphere. What's the flip side of respiration?
Sorry.
Photosynthesis. Plant growth, plant burial. Okay? Photosynthesis, primary productivity is obviously the key one. We can also remove CO2 from the atmosphere through weathering, growth of corals, for example, dissolution in ocean water, as I've mentioned. One of the key processes by which CO2 and other carbon species get into the ocean is through direct dissolution into seawater. And then things like warming affect that as well. So there's lots of different processes that you could investigate. Things like photosynthesis, respiration, being the flip of each other, are important. Fossil fuel combustion, and so on.
Where would, something like burial, all this talk about capturing carbon and sinking it into rocks, etc., what process is that?
Well, that would be removal from the atmosphere. Carbon capture and storage, they're looking at a range of physical, biological and chemical processes to remove CO2 from the atmosphere. So it might be you plant a load of biofuel crops, you chop the biofuel crops down, turn it into charcoal, and it's locked up.
Right.
You might do it through direct air capture.
Yeah.
So again, this is been tested in the laboratory in a small scales. You put scrubbers on fossil fuel plants, for example, and you directly capture it from the air. It's technologically very challenging. And it also might be chemical weathering. It's a great news story from Iceland this last week or so, where they're looking at direct injection of captured CO2 from CCS plants into igneous rocks, which stores it and locks it up over a long period of time. So geoengineering, in fact that's what we're looking at, and carbon capture and storage are ways of storing carbon and removing carbon from the atmosphere, locking it away. But there are many, many challenges in terms of scientific policy and governance, their effectiveness.
So did you say it was in Iceland?
I think it was Iceland, wasn't it? Yeah. I've actually got it on the slide a few bits later on.
You just mentioned weathering as a removal process. How does it work as a removal process?
So through the process, I didn't put the equation up, but the process of chemical weathering breaking down actually takes in CO2 as part of that chemical equation. It locks it up into the detritus that then gets washed down through rivers and stored into the ocean. So one of the big things, certainly in the quaternary literature and the kind of geological literature, is how tectonics interact with the climate through large-scale orogenic activities. So things like the Himalayan uplift of the last 60 million years or so they can look to see how that tectonic activity has affected climate through drawdown of CO2. So there's some really great work by Maureen Ramo in the States, Bill Ruderman, and others looking at this drawdown of CO2 through chemical weathering.
What's it weathering?
Just
what rock types? Because obviously we think of it weathering limestone and therefore releasing. You think of
Well, silicate weathering.
So silicate.
Silicates,
Okay.
igneous rocks, whatever. Again, I'm not certainly not an expert in.
like felspar, for example, in hydrolysis. I mean, does that?
That's outside of my bit outside of my expertise at the moment. But that's certainly a process by which it can. Certainly look at the geological literature, look at the quaternary literature around tectonics and the kind of the real big picture on climate change. So another great resource that's available out there to kind of evidence and show anthropogenic activity and show changes to the atmospheric chemistry is the Mauna Loa CO2 trace. Anyone seen this diagram before? It's quite a famous one. So this is taken from an observatory on Mauna Loa in Hawaii. Started by kind of Ralph Keeling in the late 50s, and every year, without fail, the CO2 levels, the CO2 concentration of the atmosphere have been increasing. Okay, there's no way of addressing that in any other way. In the top right-hand slide, this is just the latest monthly statistics from Mauna Loa, showing that the atmospheric concentration was nearly 408 parts per million, whereas last year it was 404 parts per million. Pre-industrial levels is around about 270, 280 parts per million. So it's a really good resource, really good graphic to evidence the change to anthropogenic activity over the last 100 or the last 60 years or so, but it's part of a larger suite of records and proxy records to show much longer term climate change. I haven't got time to show you this, but again, a fantastic resource is the Carbon Dioxide Information Analysis Centre, which is based out in the States, and they record a lot of kind of national and regional assessments of carbon emissions, and in it we can spatially map and through time. Actually, you know what? I'll just show you it. It's easier. Oh yeah, sorry, we'll ignore that for the time being. So anyway, this is just a spatial map and an intensity map of emissions over the last 200 years or so. So this is back in the Industrial Revolution across Europe, also America and Asia. And it's a great visual tool to show how the Industrial Revolution came in Europe, how it's progressed through time, and how certain areas are different to others. So it kind of really does show the spatial variability in CO2 emissions around the planet. We'll just fast forward it back, rewind it back to North America. We're a little behind the curve. You can see these pulses and waves, and you can link those to certain economic activities, such as the Great Depression, political activities, and changes to oil prices, for example. World wars can all be seen in that pulsating and changing nature of some of these regions. I think we've also got the Asian side of things, and this is just staggering. (1891), 1901. (1940s), flip. And just that intensity. And the rise of China in the last decade or two.
Is that showing total emissions or per capita?
I can't remember now. CO2 emissions from fossil fuel and cement production, million metric tons carbon. So it's the absolute values. So So that's a great way of kind of showing the emissions, but also you can link it to the social, the political as well. So I'll just kind of flash through some of these slides. This is one of the latest emissions and the projections for the next couple of years, showing that we'll continue to grow our CO2 emissions in recent years. One thing that's often asked is, well, how do financial crises and economic shifts affect CO2 emissions? They do have a temporary effect on anthropogenic emissions, but only for a couple of years or so. So we can note dips in global CO2 emissions relative to the oil crisis, collapse of the Soviet Union, global financial crisis of 2008 or so, but it does pick up relatively quickly after that. So there's a whole raft of discussions that you could have surrounding kind of the policy and governance side of things as well. And again, the Global Carbon Project breaks it down by regions, by blocks. That slide needs changing as of this morning, EU27. And it breaks it down by fuel type, ad infinitum, ad infinitum. So it's a great resource to use with your students to look at trends, look at changes, and start pulling apart some of the subtleties in perhaps the global signals. So atmospherics, you can break it apart looking at the stores, the flows, the transfers into and out of the atmosphere, and look at some of the trends in time and in space.
One thing, sorry to interrupt.
Yeah, no.
One thing that's often thrown back as well, how do we know that that's anthropogenic CO2? What evidence is there? Is it just isotopes, or is there more to it?
Well, we then get into a much bigger discussion about the cause and the role and the contribution of anthropogenic activity to global warming. It's a much bigger debate. We don't have time for that all today, which is my way of ducking the question. But the consensus, certainly in the academic literature, is 99% consensus in the peer-reviewed literature. Intergovernmental reports like the IPCC can show and evidence that the rate of change, the type of change, the regional differences are over and above what we would normally see at a natural baseline. Does that kind of answer the question?
No, it's just that often you quote the carbon isotope ratios and say, well, actually these are from combustion, therefore they're not likely to be natural sources. Just wondering if there's any more literature out there.
Yeah, I mean, there's lots of different ways of apportioning those fossil fuel emissions and kind of tracking and tracing them. You can use isotopes. You can look at different relative proportions of oxygen, nitrogen, and carbon in the atmosphere. You can CFC emissions and a whole range of literature. But the consensus is it is happening. It is our fault. The latest IPCC had the strongest language possible. It is extremely likely that the rate of change over the last 1,000 years is down to anthropogenic activity. We could go on all day. And I do this for a 12-week course with my third years. So we can look at the ocean carbon cycle as well. We can look and break that down into different components. And we were talking a little bit earlier on about the relative sizes of biological versus inorganic carbon in the ocean. And it's very important to note that it's not just algae, it's not just dead critters, it's also dissolved CO2, it's direct dissolution of CO2 from the atmosphere into the ocean. It's formation of carbonates and limestones, and the picture is rather complicated. So it's something that, again, I don't know what the specification says, but I think it suggests you look at the different spheres and look at different processes going on. Now, ocean chemistry, again, it's not my thing, but it is a nasty, complicated processes. But there was a report a few years ago by the Royal Society which looked at ocean acidification, it looked at a range of different things, but it talked quite nicely about the processes and the mechanisms by which CO2 and carbon gets into the ocean. So there are three main mechanisms by which it gets into the ocean. The first of which is solubility pump, so the direct absorption or release of CO2 into seawater. So at that sea-atmosphere interface, depending on things like temperature and pH and a range of other factors, CO2 can directly dissolve in water. Second one is biological, so fixation of carbon through photosynthesis and algae, for example, and that algae then dies and decays and falls through the ocean column into the deep sea. And there is a third pump which does the flip side. So in the formation of calcium carbonate, you actually release CO2. So there are a couple of mechanisms by which CO2 gets into the ocean and another mechanism by which it can be released. Again, this is in the IPCC, and there's also, I think I've got a link to the Royal Society report. And it shows how, certainly the solution pump or the solubility pump, in cold water, CO2 can be directly dissolved in the water, so you often see large concentrations of CO2 in cold sea waters, whereas if you have warm upwellings of tropical water, for example, that would be degassing CO2 to the atmosphere. Organic carbon pump and the calcium carbonate counterpump. So one of the concerns, certainly, that question earlier about the red line in the oceans, is if we warm our oceans, if we warm our oceans and seas due to global warming and anthropogenic climate change, we'll end up being less able, or the oceans will be less able to store that CO2, and it'll have to degas, and it'll have to go somewhere, and that somewhere will be the atmosphere. So there's a big concern around kind of what happens to that solubility mechanism. And one thing we often forget when we're talking about climate change, or it's the ugly sibling or the ugly cousin, some people like to call it, of climate change, is ocean acidification. The input of CO2 to the oceans alters the ocean chemistry, and since the Industrial Revolution, the pH has dropped by 0.1 units. It doesn't sound an awful lot, but it's actually about a 30% increase in the hydrogen ions in the oceans, causing mass mortality events around the world, and it's only going to get worse. The reason why is the ocean system takes a long time to respond, and some of the modelling by the IPCC shows that even if the emissions were to peak towards the end of this century, the concentration of CO2 in the atmosphere won't peak and drop until later in the early 22nd century. And the really, really worrying thing is that the pH, or in this diagram, the change in the pH of the surface and deep ocean will take many thousands of years to respond. Okay? We've got a pH change in the surface waters in 2250, so 150 years or so from now, of around about 0.7 pH units, a massive shift in the ocean chemistry. And this is leading to changes that haven't been seen, certainly in hundreds of millions of years, and the rate of change is unprecedented. So ocean acidification, we can directly link it to carbon processes. We can look at the solubility of CO2, we can look at how that responds, and we can also look at the effect that will have on ocean organisms, the kind of the usability, the ability to take resources from the ocean, for example, fishing and what have you, coral reefs. We've all seen pictures in the recent press about mortality events in reefs around the world recently. This potentially could only get worse. So here we go, this is the Royal Society report. Again, it's freely available online. I'll put a link in the documentation afterwards. Oh, here we go, this is it. So how will the oceans respond to climate change? This is something that can really get people interested and kind of worked up things. So increased temperatures potentially could increase photosynthesis. Great, fantastic. But it will also alter the way the ocean is structured. We'll have greater stratification between the upper and lower oceans, reduction in those important nutrient upwellings, which could then in turn affect life in the upper parts of the ocean. Increased CO2 is going to acidify the ocean. We've seen the modelling from the IPCC, but there's going to be a reduction in calcification. There'll be stress on multicellular organisms. We'll also have thermal expansion, sea level rise through the warming of the ocean. So not directly carbon, but kind of caught up in the bigger global change picture. So that's a quick flash through atmosphere and biosphere.
Sorry, just before you move on, has anybody done any work on possible feedback with the addition of cold meltwater into the oceans?
In terms of
Impacting on your acidification and your ability to reabsorb CO2?
I don't know, is the honest answer. Oceanography is not my thing. I suspect it probably won't make an awful lot of difference.
Too little water, too much ocean.
Yeah, and that addition of, I'm assuming you mean meltwaters from
Ice caps,
Greenland
ice caps, that sort of
that
stuff.
would be the trouble is the negative would totally outweigh any kind of. Again, it's not my area. But interesting point. Biosphere. This is my area. So as I said at the start, the biosphere is an area which is very sensitive to change, both anthropogenic land use management, anthropogenic change, but also the fluxes, the natural fluxes of carbon between the atmosphere, the oceans, atmosphere and the biosphere are large. Okay, they are natural processes that are going on, photosynthesis, respiration. So the biosphere is a great place to look at processes, looking at the carbon cycle. And the important thing, it's accessible. We can walk out of our door, walk out of our classroom, and go and look at forests. We can go and look at peat bogs. We can go and look at grasslands. It's a bit harder to go on a visit to the atmosphere, a bit harder to go on a visit to the oceans. So the biosphere is a great place to study the carbon cycle. So when we talk about the biosphere, we're talking about all living biomass, so animal, vegetable. We're looking at the dead biomass as well, so decaying, decomposing material, detritus, litter, and the like. The soil, okay, the forgotten part of the biosphere, as I always say to my third years, as a soil scientist or someone with a keen interest in soil science, it's often kind of neglected. It's the stuff, it's the dirt under our feet, but actually there's a hell of a lot of carbon locked up there. The inorganic component as well, a bit of calcium carbonate, depending on where you are in the world, and the fauna as well, okay. Living biomass, we also think about us and organisms. We are part of the carbon cycle, okay? Living organisms. The reason it's in brackets is I don't discuss that in the class. So when we're studying, when we're thinking about the biosphere, we can look at a lot of different ways of chopping the biosphere. We can look at the different pools of carbon. We can look at the amount of carbon stored in trees, the amount of carbon stored in soils, the amount of carbon stored in grasses, and so on. We could also look at the different types of organic matter available and present in the biosphere. So we can look at the different kind of real chemical differences, carbohydrates, lignins, lipids, proteins, black carbon. Another pet project of mine is black carbon, the product of fossil fuel combustion and fires, for example. So we can break it down to the cellular level, the chemical level, if we wanted to. But the important thing, regardless of how we break it down, is about how carbon is transformed and moved within the biosphere between the different carbon pools, and importantly, how it moves out of the biosphere or into the biosphere through other processes. So how does carbon transfer between the reservoirs in the biosphere? Well, the first one is the generation of carbon. So through photosynthesis, gross primary productivity, in plants, we can lock up carbon from the atmosphere into organic matter. We can transform that carbon, okay? We could, that carbon can change in terms of its kind of chemical structure depending on how it's allocated within the plant. So it might be allocated to more kind of lignin, woody material as opposed to kind of the leafy, perhaps more cellulose-rich material. It can be consumed, it can be transformed through herbivory. So sheep eating grass, for example, will transform carbon from one form to another. They'll eat it, they'll consume it, that carbon will be reallocated within the sheep, and part of it will end up back on the landscape. And finally, oxidation. Okay, so decomposition and decay. So we were talking a bit about deforestation earlier on, but the natural process of decomposition and decay. Respiration through for plants and animals, and non-biogenic oxidation as well. So fires. Okay, we've touched a little bit on fire as well. So the key thing when we're thinking about the biosphere is what are the mechanisms, what are the processes that transform and move carbon within and out with the biosphere. And then what are the controls on those processes? Okay, what controls decomposition rates? What controls photosynthesis rate? And how do different controls alter in time and space? One of the ways that is used quite heavily nowadays to kind of conceptualise carbon in the biosphere, or carbon in any sphere particularly, but in particular the biosphere and in an ecosystem, is what's known as a carbon balance or a carbon budget. And in it, we take an ecosystem, so a woodland, a grassland, whatever it might be, and we look at all the flows of carbon into and out of that system. Okay? Okay, so we can conceptualise it. We put a box around an ecosystem, and we look at all the different fluxes of carbon going into and out of that system. I love this diagram only because it's got a giraffe for no particular reason in the image. So carbon balances and carbon budgets are kind of de rigueur in the academic literature, and we can create carbon budgets for a whole range of different ecosystems, and one of my research areas is creating or looking at carbon balance and carbon budgets in peat bogs here in the UK, and we'll look at an example later on. But we can do a similar thing for forests. You could go to a forest, look at the size of the trees, look at the carbon stored in the trees. You could do some estimation on the rate and the movement of carbon through photosynthesis, through respiration, and so on. Don't worry too much about that. So we want to know, when we're doing carbon balances, all the different processes and different pathways that carbon can be moved into and out of the ecosystem. So for example, in this diagram, we've got photosynthesis, okay, being the primary fixation of carbon. Soil respiration, plant respiration. We also mustn't forget it's not just about gases, okay, it's also about movement of carbon through the fluvial system. So erosion of the landscape will move carbon from soils into rivers into oceans. We can also have dissolved carbon, okay, so the brown water that if you're walking in the peaks or in Snowdonia or Lake District, some of the brown water you might see washing off the landscape is that dissolved carbon coming from peat bogs and the like. So if we look at all the different processes and the different pathways, we can start summing them together to get an estimate about how carbon is behaving in that system. And it might be that you can measure some of these different pathways. It might be that you could measure some of the dissolved carbon in river waters coming off an ecosystem. It might be possible to measure plant respiration or make some estimates of plant respiration. So you can look at pathways, sum them all together, and look at the overall balance. So this is just a schematic for a carbon budget for a peat bog here in the UK. And if we want to know the carbon balance of this peat bog, we need to know how much is coming in through primary productivity, how much is coming in through rainfall, a tiny proportion comes in from rain, how much is coming from underlying weathering of limestones, for example, and then how much is released through CO2, so how much is released through methane, dissolved CO2, and other fluvial pathways like particulate losses, dissolved losses, and the like. And we can do similar things for ecosystems that aren't peat bogs. They're forests, we can look at grasslands. They all do similar things. They're all looking at pathways, they're all looking at processes. Some may measure all of the pathways, some may measure only a few. But they're all trying to assess the carbon balance of a system. So how do we do it? How can we measure carbon balances? We can go and measure things directly, and we can measure things remotely. So this kind of maybe brings a little bit of the GI science into it as well. Certainly when mapping and trying to estimate how much carbon is in forests, for example, or different ecosystems, we can use remote sensing, we use satellite technology, and lots of complicated algorithms that I still don't understand. So look at a landscape scale estimation of total carbon stocks in a forest, for example. But that's only an estimate, it's only it's a very large scale coarse image. What we often have to do is then ground truth that with local measurements, so bottom-up approaches by going and measure the carbon locked up in forests, in particular patchworks, different ecosystems. And often it's the kind of the best of both. You can get both involved, do your remote sensing, go and ground truth it, and estimate the amount of carbon in the trees at ground level. And it's this bottom-up approach, certainly when measuring forest carbon stocks or measuring the amount of carbon stored in peat, that's a really accessible way of kind of starting to get into carbon balances and so on. So it might be that you could take your students and go and measure the growth of trees or the size of trees to measure the carbon stock in that woodland. It might be that you could go and measure the local field and see how much grass is stored in the field, or whatever it might be. And then we've got to keep remembering that this storage of carbon in the atmosphere, in the biosphere, is spatially very variable. Okay, as we can kind of imagine, tropical forests store different amounts of carbon to temperate forests. Tropical forests around the world have problems of deforestation, so leading on to land use change and so on. So this is just a diagram. Don't worry too much about the numbers or what it all means, but here we have the amount of carbon stored in Canadian, North American forest being dwarfed by that stored in tropical forests. But on the flip side, we've got deforestation from these systems as well. So there's a spatial heterogeneity to storage of carbon in forests around the planet. Any questions on that? So that's kind of a really quick overview of some of the key things that I think that are important to kind of bring together a whole range of processes, mechanisms and pathways. One of the things in the DFE specification looks or talks about feedbacks being part of that kind of, what did Martin call it at the beginning, kind of geography, big picture type thing, feedbacks, thresholds, all that kind of thing. So feedbacks are very important in the climate system, feedbacks are very important in the carbon cycle as well. And the two kind of go part and parcel together. So there are a couple of feedbacks which are important. There's a whole raft of this. There's chapters out there, there's books out there on feedbacks in the carbon cycle and the climate system. But just to remind, positive feedback acts to enhance the initial input, whereas a negative feedback acts to reduce that initial input. So I'm going to show you 3 positive feedbacks related to carbon, related to future change, and how that might then impact our future climate. First of which is respiration. It's a natural process, it's happening all the time. But under future projected changes of increased temperatures, there's various different feedbacks, okay, and non-linear responses, and that's the non-linear side of things is rather important. So increased temperatures will increase plant productivity up to a point. There's a caveat there as well, but we won't go into that today. But also it increases soil temperatures, it increases microbial activity, and that increased microbial activity will lend itself to increased soil respiration, increased plant respiration, but particularly soil respiration. So this is a diagram from a classic paper back in the mid-90s, and basically it shows as temperature increases, we get a non-linear response in the respiration rates of soil. So we get, it's not a simple case of by every 10 degrees you go up, it's a similar amount in the respiration rate. It's a non-linear response. And we see this in a whole range of different soil types around the world, that with increased temperatures, we've potentially got a large response or a non-linear response to changes in those temperatures, and therefore a greater respiration rate. So the non-linearity and this kind of concept of small changes affecting a large change are very important when we're thinking about feedbacks. I'll talk a little bit about thresholds as well. So respiration rates potentially will change at a greater rate than temperatures. Permafrost meltings. Again, it's often mentioned that that's one of the kind of the ticking time bombs of climate change, is that all these frozen permafrost soils around the northern pole are a massive store of carbon. Okay, 1,700 petagrams or 1,700 gigatons of carbon are stored and locked up in frozen soils around the Arctic. A hell of a lot of carbon. Okay, and at the moment it's all insulated by layers of ice and moss and grasses and everything's hunky-dory. The problem is, with the rising temperatures, that upper surface melts, that insulation effect disappears, microbial activity, which does happen, does occur in permafrost, the microbes start to wake up and go, oh hey guys, we can start munching on this store of carbon. And suddenly we have a large, potentially a very large injection of CO2 to the atmosphere, and methane and other greenhouse gas effects. So that's a real worry that the permafrost will melt, this insulating cap will disappear, and the carbon locked up in these permafrost soils or jelly soils or cryosols will be released to the atmosphere. So one of the things that I bang on about in my third year course is about thresholds and kind of tipping points in systems. So tipping points, again, it's something that is very important to consider, is a slight shift in the system, slight modification could lead that system to shift into a brand new state. Okay, so subtle shifts, changes to temperature, changes to drying rates, whatever it might be, in the permafrost, for example, could move that system into a brand new state, brand new stable state, just not a state that we're after. So there's a lot of literature, a lot of kind of good, accessible stuff about threshold concepts, and there's a great TED talk by Johannes Rockström a few years ago, talking about these threshold concepts and how moving from one state to another might only take a little nudge, it suddenly shifts into a new system. I'll put that link up later on. And similarly, methane hydrates, these are methane locked up in ice crystals or crystal lattice at depth in the ocean. Again, a similar thing to permafrost, increased warming of sea temperatures and ocean temperatures could destabilise these large stores of methane. So, geography and the carbon cycle. Hopefully, just from that relatively brisk overview, we can see that geography has a very important role to play in understanding the carbon cycle. Okay? I wouldn't be here today if I didn't believe this. Scale is very, very important. Local scale, regional scale, global scale. Temporal scale, we can look at changes through time, we can look at changes in space. It's complicated. Okay? Again, one of the things I always emphasise to my students is it's complicated. It's not rocket science, but it's complicated. There are lots of kind of interactions, lots of feedback, lots of concepts out there. But they're all very important. They all link together. So this links to the core concepts in the DFE syllabus, into the specifications of systems, feedbacks, thresholds, and so on. And it's a contemporary current issue. It's ongoing climate change, political discourse and debate about how we manage our land, what we want our landscapes to look like, who are our landscapes for, all have a bearing on the carbon storage in those systems. And these are just a couple of stories that I picked out from the last couple of days from a range of different outlets. So there's the Iceland carbon dioxide story in the Independent. Maldives are urging people to ratify the Paris Climate Agreement due to rising sea levels and bleaching of corals and what have you. That was in The Guardian a few days ago. And the National Geographic just today talking about how forest fires and the release of carbon from those systems can have a substantive effect on atmospheric chemistry. So you can pretty much dip into any newspaper on any day of the week and find a story related to the carbon cycle. It might be direct, talking about a particular thing like fires. It might be indirect, broader pictures about global change. But I can almost guarantee you'll find a story that you can link directly to your teaching. So a few just quick examples, just to remind us of how it's an important current issue. Tropical deforestation, we've picked on this before, reduces the uptake of CO2, there's the degradation of the forests themselves. 7 million hectares a year are lost to deforestation around the planet. That should say 2000 to 2005, that wasn't an instantaneous 2005 one. There are some positives, potentially a slowing rate, but a large portion of our landscape is being deforested. There are direct effects of land use change on the carbon cycle, so land clearing and degradation. We've not really touched on the hydrological cycle, but alteration to land management, alteration to land use will alter the hydrological cycle, will change the runoff regime, will change the evapotranspiration regime, and that will also in turn affect biogeochemical cycles like the carbon cycle as well. Amendments of fertilisers, excess nutrient loading through agricultural land management, again, is going to be a direct effect of land use change, and that effect will in turn affect biogeochemical cycling as well. And I really got into this land modification thing the other day when I was preparing for this. I was trying to find some real headline numbers to kind of emphasise the importance of this. Around about half of our land, just over half of our land, planet surface has been modified by humans in some way, shape or form. Croplands, pastures. 7% of our land has been affected by, or has been impacted by human infrastructure. Okay, roads, railways, electricity generation, whatever it might be. Around about 80% of the land surface has had some kind of direct influence. It might be population, might be roads, whatever it might be. And yesterday, I was reading this, there's actually a paper out yesterday talking that there is no place on the planet that hasn't been affected by anthropogenic activities, direct or indirect. And this was staggering, what I found as well, was around about 25 to 40% of all primary productivity, all photosynthesis, is in human hands, through agriculture, forestry, and so on. So here we have a direct link between anthropogenic activity and the carbon cycle. Okay, nearly 40%, slightly older number, 25% is the 2013 number. A big chunk of primary productivity and photosynthesis is in human hands, been appropriated, is the term that they use. Land fragmentation, soil erosion, these are major global problems that have direct relevance to the carbon cycle. And we need time. Has anyone come across the concept of ecosystem services before? Some people may have done, some people may have not. This is a concept that was popularised by, it's been around for a few decades now, was popularised by something called the Millennium Ecosystem Assessment. And it's basically a way of defining, a way of kind of structuring the benefits that people derive from the natural environment. And these are the different ways that ecosystems and the environment give us things, okay? And that might be provisioning things, it might be regulating things, supporting activities and cultural activities. Some examples, provisioning. Okay, the ecosystems can provide us timber, it can provide us food, it can provide us fuel, for example. Regulating, okay, regulating climate through the carbon cycle. Cultural, there's an aesthetic value to the natural environments and so on. So the Millennium Ecosystem Assessment really popularised the term of ecosystem services. And importantly, within the ecosystem services framework is the idea of climate regulation, of supporting nutrient cycling, primary productivity, soil formation, all keep coming back to the carbon cycle. So the carbon cycle can be thought of, or carbon in an environment can be thought of as a valuable service. Okay? There's a way that some people have been arguing that we should protect our landscapes, not just from their intrinsic aesthetic beauty or what they provide in terms of fuel, but a much wider suite of services, so we can quantify how much carbon a peat bog locks up. We can value that, we can start putting numbers on that, and in doing so we can perhaps protect those landscapes. There's a big debate about whether or not that's the right or wrong thing to do, but that's the way things are going. So we can use it to look at land trade-offs, and part of these trade-offs we can be thinking about carbon. We can think about the biogeochemical cycling, carbon sequestration in a landscape, for example. So in this example from one of John Foley's papers, we've got three different systems: a natural ecosystem, an intensive cropland, and a mixed system. In the natural ecosystem, all these ecosystem services are maxed out effectively. So forest production, carbon sequestration, water quality regulation, they're all really good, except for crop production. Okay, if you're a farmer, that forest provides nothing to you. If you're an intensive cropland, if you're a farmer or a producer, you can get a lot of crops out of that. It's an ecosystem services, but all the other ones are down to a bare minimum. So it's a way of kind of trading off different land managements, different techniques, and kind of hopefully bringing about the best. And here we've got kind of a balanced system where we've got crop production, we've got carbon sequestration, and the other ecosystem services. So it's a kind of real high-level concept, but it's a way of kind of valuing ecosystems and at the same time quantifying them. And importantly, for our purposes, carbon is explicitly mentioned, or nutrient cycle, carbon cycle, regulating is part of that value system. So, scale. Okay, we've talked a little bit about scale. We talked about scalability of systems, and Martin mentioned that at the very start. Certainly, the carbon cycle is a great way, or it has many opportunities to look at the global system by looking at local activities or local processes. And just an example, in the second year of their studies here at Manchester, the students start to think about the dissertation. They start to think about what they want to spend a substantial part of their third year studying and investigating. And I often get students coming to see me and say, right, Gary, I want to do something on climate change. I want to do something on the carbon cycle. Okay, great. What is it? then they freeze. They don't know how to break down the big picture and look at a small subsystem. Many of them want to solve climate change. I'm going, fantastic, but do you have a global climate model in your back pocket and a supercomputer to do the modelling? No, I don't, Gary. Well, what you can do is look at a specific component, a specific pathway, a different process, a site-specific location. So it might be you can go and do a carbon budget of a local forest and see how that responds to change. Or compare a degraded system to a pristine system and how they compare. So this is a great way of taking students, taking them out into the local area through fieldwork, or even just out into the playground or the local field, whatever it might be, and looking at processes at a very local scale to kind of then start thinking about the big picture. So it might be that you go out into the local forest or the local farmer's field, and in that farmer's field you start making an assessment of how much carbon is locked up in that year's wheat crop, for example. Go out, throw some quadrats, bring some samples back, weigh it, measure it, whatever. And you're adding to the knowledge of the carbon cycle, but you're not trying to solve the entirety of the carbon cycle. So scalability is very important. And in the last, I've got about 10 minutes left. I'm just going to give you an example, a case study that is close to my heart, my research field. But it's also in, I think it's in one of the specifications as peat bogs, and there's other specifications. I think there are specific examples of tropical forests, I think, or grasslands. The same thing applies to whichever ecosystem you're in. You could look at a specific ecosystem and break it down to its subcomponents and start investigating the carbon cycle therein. So peatlands, okay, peatlands are very important. They store an awful lot of carbon because they're an accumulation of dead organic matter that is inhibited from degradation through waterlogged conditions, low temperatures, low pHs, and the upshot is that organic matter that is decayed from mosses, from grasses, from shrubs, whatever it might be, doesn't degrade, and over time that peat builds up year on year for the last 10,000 years or so. It's got a very high organic content, large proportion of peat, around about 50-55% is carbon, okay, large store of carbon in peatlands. And peatlands around the world, which is a very old diagram, are distributed pretty much across the entirety of the planet. We've got northern hemisphere peatlands, so places, northern Canadian boreal shield, Russia, Scandinavia, the UK, lots of temperate peatlands, also some temperate peatlands down in Argentina and South America, and a few in Australia. I always get reminded at conferences and meetings that Australia does have a few peat bogs. We've also got tropical peatlands spanning the planet, so Amazonia, central belt of Africa, tropical peatlands in Indonesia, and so on. So it's a real global soil type, a global ecosystem, and we've got it here in the UK, which is a very important thing. And they're climatically determined, okay, so they require a certain amount of rain, they need lowish temperatures, and very wet days for them to form. And future change and future climate change is going to move the climate envelope back, and effectively, potentially, we could see the demise of certain peatland systems here in the UK and elsewhere as the temperatures start to warm, we start to dry out, and so on. So in the UK, we have soil carbon in the UK somewhere around about 10,000 megatons of carbon. Okay, and most of that, or a good chunk of it, 50% or so, is stored as peat in Scotland. Okay, so Scotland has the lion's share of carbon in our peat soils here in the UK, but we do have some in the Pennines, in the Pennine chain, Peak District National Park, parts of Wales, down to Dartmoor and Bodmin down the southwest, and the fens of East Anglia and Cambridgeshire. So we've got a lot of carbon stored up in peatlands around the country. The worrying thing is future climate change scenarios suggest that we're going to get warmer and drier. So what's going to happen to these systems in the future? So it's important to understand the responses of peatland systems to erosion and climate change. And it's not just future change that's important, it's past change as well. So past land management, past environmental pollution has affected peatlands around the country. People familiar with the Peak District? You guys are all kind of northwest-ish geographers. Okay, so Peak District National Park, fantastic location to go walking. If you've ever been walking out on the Bleaklow Plateau or the Kinder Plateaus, you've probably seen some dark-looking peak hags with little vegetation, erosion down to the bare mineral soil out there. That's partly through past land management, partly through environmental pollution, so the Industrial Revolution kicked off here in Manchester, and part of that led to deposition of heavy metals and so on. And basically we've got a knackered system up in the Peak District. So we've got a knackered system, but there is some hope. There is some hope for future change. So revegetation and the interaction of vegetation and soil types and land management potentially could lead to a positive. So the peatland system is a great location to look at change, both in terms of historical change and the effects of historical change, as well as future change as well. So what can we do in these systems? What can we measure? Well, we can go out and we can measure the amount of carbon in the water, we can measure the amount of carbon in terms of gases coming from these systems, so CO2, methane and others as well. And like before, we can create carbon budgets. We can sum all these up and see whether or not these carbon-rich systems are in equilibrium. Are they sequestering carbon? Are they a sink of carbon? Or are they a source of carbon? Okay? Are they losing carbon more rapidly than they can sequester? And it's a big debate at the moment in the UK literature and the international literature, is where are our peatland systems which are healthy and sequestering carbon, and where are our broken systems that are losing carbon to the atmosphere, to the fluvial system, and so on. There are different controls on peatland systems, and if we had a bit more time, we could have gone through these perhaps. But one of the exercises I do with my third year class is how do these different controls, these different driving factors, how could they affect peatland systems? So how could future temperature change affect the stability of this ecosystem? How could land management, so overgrazing or undergrazing? How could fire, so traditional land management in the UK uplands has fire as part of that component, or wildfire, for instance? Or land management restoration and revegetation, how will that affect the carbon balance? And what's really good is that research in the UK over the last 10, 15 years or so has led to the peatland carbon code in the last couple of years. This is a voluntary standard for peatland restoration projects which aim to evidence their effectiveness in terms of sequestration of carbon as a way of trading it on the carbon markets, i.e. getting an economic return for restoring these landscapes. So it comes back to the ecosystem services approach a little bit. If we can value these ecosystems in terms of a commodified unit, i.e. carbon, we can get money in for restoration, we can protect these ecosystems, and we can restore them and revegetate them. So we've kind of run out of time a little bit, but I thought a couple of little exercises to throw into the mix for this afternoon. We heard earlier that rivers is now out of the kind of the limelight, but let's put it back in a little bit. We all know how to kind of go and measure flow in rivers and what have you. But if you combine that with knowing something about the chemical makeup of that water, if you know the carbon content of that water, you can start to estimate the amount of carbon leaving an ecosystem. You can start to measure that flux of carbon coming out of an ecosystem. Equally, we could do something with measurement of trees, allometry or allometric relationships between simple measurements like the height of the tree or the diameter and the circumference of a tree are easy to relate to the total biomass and therefore the total carbon stock. And it's a great way, really simple way of going out, doing a field measurement, measuring a woodland, for example, and calculating the amount of carbon in a forest or a woodland, for example. That was my 2 pennies worth of a couple of ideas. So for me, the carbon cycle is inherently geographical. Scale is important and scalability is important. We know some of this already. It's not a particularly scary or complicated thing. And it's all linked into a whole range of the systems thinking. And it's a contemporary issue, something that's going on now, something we can relate to, and we can talk to our students and bring examples from the media and elsewhere. So those are my kind of 4 take-home messages from the session this morning. Has anyone got any questions?
Yeah, just on a peat idea, if the moorlands became vegetated with trees again, would that increase their carbon store relative to the peat? I assume it would then.
So, we're on to the rewilding question of the UK a little bit. Yes, they would increase the amount of carbon stored in the biomass, in the above ground biomass. The problem with planting trees on peat is you alter the amount of carbon stored in the peat. Okay? Forests, it's a complicated dynamic between storage of carbon in the above ground biomass, the amount of storage that's stored in the peat. Trees tend to need drainage, they tend to be a little bit drier, a bit wetter, so you end up having to drain a little bit of the peat, and part of that carbon is lost. It's the balance between where do you want your carbon being stored, above the ground or below the ground in the soil. So afforestation on peats or peaty soils could have benefits, but it could have negative consequences as well. That's my get out. But there are afforestation projects that happened in the past. So if you go to the Flow Country in north of Scotland, there are large reserves or large plantations of old cypress spruce and pine and what have you that have had a detrimental impact on the soil and are being deforested in order for peatland to be actually come back to what it was before. But depending on where you plant it, how you plant it, and what you plant, it kind of depends a little bit.
So, for example, on Saddleworth Moor at the moment, the vegetation's growing back because they've stopped the sheep going on there.
Yeah.
So you've got trees, you've got ash trees starting to grow. They're growing quite fast actually. In the areas that were just bare peat at one time. It's changed dramatically over the last 20 years. So, I mean, is that
A good thing about
it's got to be a positive thing, sure.
Yeah, I mean, again, it comes back down to scale. It's got to time scale. So in immediacy, planting vegetation on bare soils and bare landscapes is good because you arrest the erosion, you stabilise the surface, but over time, are you going to impact on the stock of carbon in the soil and the peat relative to where it was before? So in the short term, revegetation is great, but you're shifting into a brand new ecosystem. Is that better or worse? I don't know. We don't have the time scale to know that. But it's really big debate.
Because it was all woodland, wasn't it?
At one stage it was, yeah. Again, with time scales, this is what we can link that right back in. Yeah.
The new A level will place a greater emphasis on fieldwork, particularly independent studies. So I was quite interested in the last 2 points on suggestions for investigators.
I mean, they were honestly just quick.
How easy is it to quantify the amount of soil in say if we went to a stream and collected some samples, how easy is it to actually estimate how much carbon is within that? Is it something that a student that's 17 could be expected to do?
You could do. There are ways of doing simple. I mean, I'm thinking of peatland systems where you look at the colour of the water, browniness effectively of the water, and relate that back to carbon concentration. There are ways of doing that. It's not a simple case of looking at it and going, oh, that's 5 parts per million or whatever. But you could do that. You might have to link up with your chemistry department, for example, to do a bit of work on that. The forest thing, really simple thing. Tape measure around trees, relating it using simple known allometric constants and equations. And then from that, you do a couple of quadrats, work out the density of trees in the forest, scale it up, you've got the amount of carbon in that woodland or whatever it might be. And you can do similar things for grassland. You could go and quantitatively remove a quadrat of grass and go and measure it in the lab and work out the carbon content and so on. So there are ways of doing these things that are relatively simple. You could, say, link up with your science department and do some simple measurements, yeah.
Are there any statistics out there whereby certain vegetation is being studied like this, and therefore you can just do the concentration of that vegetation and then...
So certainly for vegetation types, you could say, right, I've got a tree, let's look up how much carbon, typical carbon concentration of that tree, or that vegetation type, or that grass type. Water's a bit more tricky.
Where would that?
It's kind of, it'll be all hidden in the published literature, but a rough back of the fact calculation is organic matter has 50% carbon in it. More or less, regardless of, somewhere between 45 and 55-ish. It's not going to make a huge difference to your calculations, but that's kind of a rough and ready value. But you can get specific values for certain vegetation types, but that would be buried in the literature somewhere. So 50% is a good estimate.
Gareth, when you're teaching your first years about carbon capture, etc., what areas do you find they have difficulties with, which may be worth focusing on at A level?
Ooh, good question. I think scale, so getting your head around those numbers, I think the sense of relative size of these different things, and understanding, right, the soil is 4 times or 3 times as big as the atmosphere, or that kind of getting a sense of the size of things. Understanding some of the detail of the processes in order to understand the big picture. I think they like to know the big picture, they like to know some of the big answers and the big questions, but you still have to relate it back down to the basic nuts and bolts of the geography, physical sciences. And sometimes that's not first thing on a Monday morning at 9 o'clock, teaching them about the hydrology or the photosynthesis pathways or whatever, can be challenging. But it's kind of getting down to the process and the nitty gritty, unfortunately, in order to then know something about the big picture. I think we've just run a little bit over time, but I'll be around afterwards as well for a little bit, and I might be able to pop back this afternoon. If you've got any questions, drop me an email. I'll see you later on perhaps as well. But thank you very much for your attention.